So we're here today to talk about the Open Images Challenge from 2019. There were multiple tracks in that challenge, and in particular, we're looking at the instance segmentation track.
You know that we're not seeing your screen, right? For your slides.
Oh, yeah, okay. We'll press the buttons for that share screen. It's the one that's not white, so your eyes just skip over it. They made it important, but instead it must not be. But now oh no, it's share. There we go. Yeah, and then the button, as windows jump around.
Yeah, we got it now.
I need that participants list in case somebody puts up their hand. I'm not looking at the chat because there's too many things. Right. So this was hosted at Kaggle, so it's definitely a Kaggle challenge, but it was also related to the ICCV conference, that's International Conference on Computer Vision. I find the computer vision conferences to be quite hilarious. They're all just like various combinations of C's and V's and M's and L's and I's. You just like sample the letters and you've got a conference. This one's an important one and a big one. I am Alexei Nozdrom-Plotnitsky. I am building vision-driven robots at a startup called Vancouver Computer Vision, which is challenging to do from home sometimes because robots, you probably don't want them on the internet for obvious reasons. If you're an amazing like ML computer vision person, like maybe we should work together. We would definitely hire the right person, and you'd be working with me, and I'd love to do that. And then this is the recent screenshot of my Kaggle profile. It's meant to show that like I know something about Kaggle. I understand how it works, and so there. Now it's justified that I might present. What we're going to do today, for people who've been to this meetup before, you know how this goes. We have like a little overview of the competition. We're going to talk about what the data looks like. We're going to talk about how we measure success. What's the competition metric? Decide who wins. We're going to talk about methods generally to solve this problem, and we're going to look at winning solutions. This is the screenshot of the competition page. Things I wanted to highlight here. 5 months old, so all this stuff is pretty recent. There can't have been too many stunning innovations in this space since we had the competition. 193 teams on Kaggle, although as you'll see later, like maybe only 40 like actually serious teams. Hey, Yves, welcome to the party. And that's like a very small number as far as competitions go. And I think the reason is this is hard. Like this is a hard problem. Like in the spectrum of computer vision problems, this is hard. And the data set is big, and the models are big and slow. And so you probably need sort of like non-trivial compute resources to participate in this competition, just in terms of hard drives and GPUs and so on. So that keeps the numbers down.
So this was definitely not a kernel competition then.
No, definitely not.
Stuff.
You'd bankrupt Kaggle using the kernels for this. But that said, like, I mean, I didn't participate, but you know, I have like what used to be $2,000 worth of hardware in the corner, but that was a couple of years ago. That would have been enough to limp in. So it's not like it's prohibitive, but I wouldn't have been able to be competitive with that. And then, yeah, like $25,000 prize money. So there was money, but like that's not a big deal. It certainly wasn't a big deal amount of money. This competition was associated with ICCV. There's a web page from the conference, like related to the competition, and there's lots of great material there, like links to slide presentations and write-ups from winners and hosts and so on. So like if you want to learn more, go there. And I mean, in fact, I got material from there as well, so that was great. I have like a link at the bottom of how to get there. I'm going to kind of drop links all over my slides just to kind of reference material for where I got it from. So this is a slide that I like to use to talk about these sort of fundamental basic problems in computer vision, to explain what instance segmentation is. I think we should all be familiar with the idea of classification. So like, you know, given a data point, assign a class to it. And in computer vision, the most basic form is like I have an image and I need to assign some kind of like image level label to this. So like if it's a photo of a dog, then maybe like the image level label is dog. We're not saying anything about maybe where in the image the dog is, or if there might also be grass in the image or something, but the label is somehow dog. One step further after that, we might localize. So here in the top left, we have sheep, like the label for this image is sheep, and we can say sort of where in the image the sheep are. To the right, we have this like object detection problem where we're kind of interested in putting bounding boxes around the individual sheep. So that would be what the goal is. We're kind of like, it's like 4 coordinates, top left and bottom right gives us a bounding box. Alternatively, in the bottom left, we have semantic segmentation, where essentially for every pixel in the image, we're classifying the pixel. And so here we're trying to separate the grass and the road and the sheep. But we're not paying attention to instances like we did in object detection, where we consider each sheep to be like an instance of the class sheep. But then finally, in the bottom right is like instance segmentation. A picture is 1,000 words, and I think it communicates intuitively that we're looking to sort of figure out which pixels belong to which sheep. So this is the hardest of all of these problems that's on the screen, and it is hard. In that sense, we'll see. We try to be newbie friendly here at this meetup, and I think there should be something in this presentation for everyone, I hope. If you're really advanced in computer vision, we might not satisfy you. We'll see. So it might hit like different people, different levels. Is that a hand in the air, Evis, or no? All right, good. He's waving now. Right. So,
but I do have a question actually.
Oh yeah.
Can we go back to that last slide?
Yeah.
So this is new to me, and I'm just trying to think through the instance segmentation, and I feel like it's a very difficult thing to define because we are going in saying we want to differentiate sheep from other sheep, but we might not want to be differentiating, like, say, blades of grass from other blades of grass, right? Like, you need to be very careful about how you define what instances you're segmenting and which ones you're not.
Yeah, and what does it even mean to be an instance? It would probably get complicated in some cases.
Is there another example that you can give that would be instance segmentation?
Pedestrians on a street?
Yeah, I mean, maybe you care about the fact that there are instances of pedestrians rather than just like pedestrians, right?
I don't know, would you? I feel like just any blob of pedestrians would be something the algorithm should be.
Once you have instances, you can start to like track them as objects and like figure out what direction they might be walking in case they're going to walk in front of you. So that's why like the individual objects are interesting. Also, like in medical applications, when you've got like slides and things like that, you'd be interested in segmenting like individual cells.
There was a question in chat, which I'll answer, which is, are you going to share the slides? And I think you already have shared the slides, right? Did you put it as a comment on the meetup page?
That's correct, yeah.
Yeah, so the slides are available even right now if you want them, by going to the meetup page and looking at the comments.
Yeah, you could read ahead.
Yeah, you could.
Right, okay, and then here are just more links to references. I stole a bunch of the next slides from these slides from the conference. Right, so the data set. So what is the data that we're expected to be training and testing on? So it's this open images data set. It has several versions. It's now on version 6, but this competition was run on version 5. It's big. They're like 9 million images. Some of these images have image level labels. Some of them have bounding boxes around objects. Some of them have segmentation masks like we've just described. And some of them have this visual relationship thing, which I'll show you in a moment. But it's like worth pointing out that not all images have all of these types. So it's not 9 million of each of these. It's less than that.
Any idea where the labels came from? These are all hand annotated, or they come out of other algorithms?
It's by hand, and they crowdsourced it. Actually, it's interesting. There's a little thing on this next slide here. One of the things that they were able to do was crowdsource it because they had these images where there weren't licensing issues. So this is open. It's all CC. So copyright's not a problem. You can use it commercially. That's pretty exciting because almost everything out there is banned from that. Where did these images come from? So this is not my slide, and I don't fully understand it, but essentially, like a bunch of this data is from Flickr, and they also had stuff from web image searches. The point is that in some data sets, you might have examples of ball that look like this. You know, you put ball into Google and you scrape the images, and now I've got a bunch of examples of ball, but those are not really real world, and it's not very hard. And open images contains images more like the one on the bottom. So this is the one that might be ball. So it's much more interesting if you want to build things that are going to work in the real world, and it's much more interesting. It should be way harder. There are image level labels in this data set. The example I'm going to talk about is the one on the left. So this image actually has multiple labels at the image level. So this is an apple image, this is a food image, this is a fruit, orange, and grapefruit image. But we can't just assume that everything that wasn't labeled here is not here, because they didn't go to that. There were so many classes, they just couldn't exhaustively check all of them against all images. But they did call out some negative labels. I'm not exactly sure how they picked them, but you can sort of have an intuition here that these are labels that like are close to the ones that are in the image, but have been specifically stated that they're not. So we know that plant, tomato, and vegetable would be wrong here. But we don't know about bowl. Bowl is essentially ambiguous. Whereas I think in a lot of classification settings, we sort of have these mutually exclusive, collectively exhaustive classes, and we always know that if it's not there, then it's not there, and so on. That's not the case here, for like just practical reasons. Like if you imagine trying to scale up to everything, like you're never going to get someone to check every image to make sure that it doesn't contain every possible thing in the world. And so we have data like this. There are bounding box labels in open images. This is a couple of examples. So we can see it can be kind of busy and complicated. On the left, we have like people and with heads and eyes and noses and hands and guitars. So there's a lot of different objects that are all overlapping. And so that can be quite interesting scene. And then on the right, kind of like a more basic scene, like cups and saucers and so on. Here's these visual relationships. I don't think this is like a big data set, but it's certainly interesting. So, here we have an example of guitars and people, but they're not just guitars and people like happening to be in the same image. There's some relationship here. Like the people are playing guitars and these chairs are at tables. And there was a competition related to the visual relationships that we won't talk about today, and I didn't read about, so someone could present 2 weeks from now. And then finally, we have instance segmentation masks. So these are 2 examples from the data set. Again, not my slides. I copied them somewhere else. And so essentially on the left, we're visualizing the mask. And so there are 2 different teapots, and there are 2 different masks, one for each teapot. And we've kind of colored the mask in on the image. So we said all these orange pixels are one teapot and all these pink pixels are another teapot. We're visualizing the data here. And similarly on the right, like that cat isn't yellow in the photo. It's been colored yellow because that's the labels that we have. These yellow pixels are the cat pixels in this image.
Do you know, maybe you're going to talk about this later, but do people generally regard the labeling as fairly accurate?
Yeah, we will talk about that in a moment.
Okay.
Yeah. So finally, like on the size, if you put it all together, there's 9 million images. What's interesting here is there are about 2.8 million masks. So we just saw 3 on the last slide, 2 teapots and 1 cat. So there are 2.8 million of those. They're on about 1 million images. So there's kind of like a 3-to-1 ratio on average. And they have 350 classes of mask, whereas like up here, for generally speaking, there are 600 classes in the data set. And it's like the largest existing data set that's got all of this. So that's pretty exciting.
These classes, do you happen to know, are they related to ImageNet classes in any way? Did they take a subset?
I don't think so. There are not a lot of breeds of dog, for example. So I think they're their own.
All right.
And so then here, this is the instance segmentation task. Here are some more photos of, I don't know, rollerblades. They might be shoes, who knows, of sandwich or waffle, I guess, banana and jaguar. And for this competition, they split the data such that the training set was 848,000 images. So this is hard. So why is this hard? Well, these are complex images. There's a fair number of classes, more than other such data sets. There's definitely class imbalance. There's a lot of some and a few of others. It's kind of diverse, and there's some complex shapes. So here's some examples of some kind of container that someone's holding. This bat is actually separated by the person's hands, and probably often is in photos. So it's interesting. In terms of how they labeled them, and this gets to Bruce's question about quality, so they actually kind of labeled it at 2 speeds with 2 methods. So for the training set to create these 2.1 million masks, like about half a minute was how long somebody spent manually labeling it. and they use the slide got slightly messed up when I converted it into Google Slides, but some kind of like interactive thing with an algorithm to try and get like quick results. When two different labelers label the same image, they agree with each other kind of like 84% of the time by one metric and like 75% by another metric. Whereas when it came to the test set, they actually spent a lot longer. So they spent a little over 2 minutes on each image. And they used this different free painting tool. And those labelers agreed with each other kind of more like 90 or 79, which I guess in some ways is, 90 is only 6 more than 84, but it also closes the gap with 100 by a large amount. I mean, it depends how you want to measure these things. It's a little abstract. But you can see these labels are like pretty good. And the test labels are better than the train labels, which is interesting in machine learning. We don't generally like it when our test distribution or our test data is different from the train distribution or train data. That kind of scares us. But it's kind of natural. I mean, you can see how it happened here, right? We had a need to sort of cheaply and scalably create a whole lot of data. But when we test our model, we want to have like a really good measure of how accurate it is and how well it's going to perform in the real world. And so we kind of, because of budget concerns, we had no choice but to do it in two different ways. And so therefore, this gap, this sort of distribution gap, domain gap exists, and we just got to deal with it. And then just here's a couple of examples of, so there's a comment there that supposedly the training data they think has a better agreement than data in Cocoa, and you can see what you might do with the interactive tool or the free painting tool. Okay, so finally, the details of the submission file are not important. The reason I have this slide in here is I wanted to point out, so what are we doing here, right? So we get an image, and for a location in that image, we're going to have a little sub-image where each pixel we're going to kind of label as being a class or not. And then finally, we have a confidence. And so you could think about these as probabilities, but they're not. They're numbers between 0 and 1. And it's up to you to make sure they're sorted. That's the most important thing. So things that are higher confidence should be above things that are lower confidence. And that's going to show up later when we look at the metric. But this is basically what you're submitting. Now I'm going to talk about what the evaluation metric is. They use something pretty standard, and we have a couple prerequisites we need to make sure we cover. Again, this will be interesting to some people and boring to others. Sorry. So one of them is the concept of intersection over union. So this is, I like this image. We have two boxes in the lower part of the image around this piece of art, I guess. And we might ask the question, like, are these the same, or are these roughly the same? Do these boxes agree? How would we measure the extent to which they agree? And what we like to use is something called intersection over union, where it's right there in the name. So we take the boxes and we take their intersection and how much area that is. And we take the boxes and we take their union. In this diagram, their union would be the light blue and the dark blue. And we take the ratio. If the boxes overlap perfectly, then the ratio is 1. If they don't overlap at all, the ratio is 0. That's pretty nice for a metric. In between, it's not that interpretable. I mean, what does 0.6 really mean? Is that good? Depends on the context, but we have a way of measuring the agreement between two boxes. It's nice. And now I have this flow chart for something we would do. So we have a bunch of ground truth masks here on the left, and we have a bunch of predicted masks that our algorithm created. And by the way, these predicted masks, they have confidences. Let's remember that. And so what we can do is we can compare all of the ground truth labels and the predicted labels and establish when they're the same or when they're not. And we use an IOU of 0.5. So if that IOU metric is above 0.5, then we're saying two boxes are the same, or two masks are the same, or two boxes. This applies to both. You can do the same computation. And by doing this correspondence, we can sort all of these things into 3 piles. We have a pile where it was in the ground truth, but there was no prediction, no matches. We have the pile where it was predicted and it matched something in the ground truth. So that's good. This is going to be a correct pile. And then finally, we made a prediction, but there were no matches. So this is like excess. This is false positive territory here. But we're not done yet. because there are confidences here, and so we can pick a confidence threshold. We could say, you know what, like all of those things that were below 0.1 confidence, like I don't actually want to submit those because those were really low, and so we can suppress those. We're going to turn them all to things that we didn't predict. And so if we did that, like so these this first pile, ground truth without prediction. So we should have predicted it, we didn't. Those are false negatives, right? We should have done it, but we didn't. So in classification terms, that's a false negative. If we predicted it and it had a match, and it was above our threshold, then it's a true positive. Like, you know, we kept it in, we didn't throw it out, we predicted it, it was a match, true positive. But if it was below the threshold, then we're gonna throw it away. But it had a match, so it goes into false negative. I know this gets a little bit like verbose and hard to keep in your head at once, but hopefully this is going. And then finally, also, our predictions that didn't have a match, so we shouldn't have said this. If it still comes through after the threshold, this is a false positive. But if we suppressed it with our threshold, this is then a true negative. And given a threshold, we can take anybody's predictions and sort them into these 4 bins. And that's great because we can start to compute metrics with these bins. And most importantly, we can compute precision and recall. So if you're studying machine learning, and predictive modeling, you need to know these things. And so precision would be true positives divided by true positives plus false positives. That is, of all the times that I said that there was something there, what % of the time was I right? And recall would be, of all of the objects that were there, how many of them did I correctly find? So that would be true positives over true positive plus true negatives. No, plus false negatives. And so we can create curves. So then this is a final concept that people should be familiar with: a precision recall curve or an ROC curve. Essentially, on this last slide here, I presented a function that computes these metrics on the right, given a threshold and given a prediction set. And if we changed all possible thresholds, then we would get all possible combinations of these, and we could get all possible precisions and all possible recalls. And we can then plot this chart. And so for every point on this line, there exists some threshold that would give us this performance. And then finally, average precision is the area under this curve. So if this is amazing, if the model is perfect, then it's a square and its area is 1. And if it's really, really bad, I think its area is 0, although we would hope to get at least like a half. And then the way we get from average precision to mean average precision is we do this independently, separately for every single class, and then we take the average. So we consider it essentially like a binary classification problem for every single class, and then take the average across 300 classes. Now, this metric isn't perfect. I got this from the YOLO v3 paper. And we should be like a little suspicious of YOLO. It's very well marketed, and he tries to make a big splash out of everything. So this is like very cherry picked, but it does get at like a weakness of mean average precision, which you like, or maybe it's a corner case, depends on your opinion. But essentially, here we have the rows are 2 different models. They say detectors. And there's 2 different images, only 2 images in this test set. And the model on top, and I don't know how good the like pixel quality is for everyone, but if you looked at the bounding boxes on the model on top, I mean, we have dog, 99%, person, 99, camel, 99, bird, 99, person, 99, horse, 99. Like, this is a perfect model. Like, we can all agree about that. It's amazing. There was nothing here that shouldn't be here. They were all bang on the object, and they had maximum possible confidence. Perfect model. On the bottom, we have like a pretty confusing jumble of boxes. The probabilities are all over the place. There's boxes that don't make any sense. We got horse and person on top of each other. Probability is near 0.5, and in fact, the horse has a higher probability than person. Like, that sounds bad. But if you actually work through this class by class, so for this bottom image, for example, dog, if we pick our dog threshold as 46, then the dog box on the right gets suppressed, and the dog box on the left gets kept, and so we had a perfect dog classifier. If our bird threshold is 90, then we suppress the bird on the left and the bird below, but we keep the correct bird. And so we also have a perfect bird classifier. And so you could work your way through all the classes in this image, and you end up with also a perfect model. And obviously, this model on the bottom isn't perfect. So there are issues here that I think are worth thinking about. But all metrics have their issues, and this is definitely like broadly accepted. Finally, I'm not going to go into these details because time is limited and attention is limited, but this is a messy data set. Like I said earlier, we've got not exactly exhaustive labels, right? So we can't really say what is and is not in these images. And so it's very hard to talk about what is a false positive. Maybe the label was wrong. And there's also a class hierarchy. So like it's not just a flat set of classes. There's like a bike helmet and motorcycle helmet, or no, well, maybe it's football helmet. Oh, there's two different types of helmet that roll up into the helmet class. And so they did some things to handle that. So there's all kinds of extra detail. There's like a whole paper about how to measure this. And I think if you're going to deal with messy real world data that looks like this, it's worth studying. But for a presentation like this, I think this concept of mean average precision is what we should cover. Right, so now methods. So these are three methods that we're going to talk about, mostly the one on the top. These are screenshots from Google searches. The links are purple because I clicked them recently. But I threw them in because there's a tiny bit of abstract, there's dates, there's citations, lots of great data all in one place. Mask RCNN is absolutely the granddaddy method in this space. That's why it's got over 5,000 citations. But these others are relevant. They all build on each other, by the way. There's been a very strong tradition of stepwise improvement over the last few years on this. And there's links there for people who want to visit the slides later. Okay, so Mask RCNN is wildly complicated. And if we wanted to spend like 1 or 2 courses covering the prerequisites and then a 3-hour lecture, we might be able to get to the bottom of Mask RCNN, but we're not going to Mask RCNN, but we're not going to do that today. What I thought we would do is we'd work through the inference procedure. Basically, like conceptually, how is this thing used? And then if we could do that, we would start to understand it. And by the way, like the training is different from inference, which is great. It's extra confusing. So if somebody shows you an architectural diagram, you might be looking at the training view and not even understanding how this thing's exactly going to work. But okay, so got an image on the left. And this is a cat slam dunking a basketball. It's like not my image, but it's great. It's a very real world image right here. And our first step, I should say, our first step is to try and get bounding boxes on the cat. All right, cat, like the objects in the scene. We want boxes. That gets us first step of the way there. And we're not going to talk about convolutions and subnetworks here or anything, but like we're going to pass this image into a neural network, and partway through, we're going to have a slightly smaller version of the image with a lot of rich information. Somehow, magically, you either understand or you don't. That's fine. The network has added a bunch of information to this image. And we need boxes. And the way in which we create boxes, this is the de facto standard. It's very unsatisfying. It's very brute force. There's got to be a better way. Someone's going to find it one day. Essentially, we consider basically all possible boxes. So in the middle is a visualization of a set of anchor boxes. So there are 9 of these here. There are 3 different scales and 3 different aspect ratios. So we have kind of like a square, a portrait, and a landscape box at 3 different scales. And we're going to consider the possibility that the correct box is one of those 9 at every single location in this image. So we're going to slide this set of anchors all the way across all the rows and all the columns. And we're going to consider thousands and thousands of possible bounding boxes all at once.
This is, sorry, slightly off topic perhaps. These bounding boxes are all, their sides are aligned, vertically, horizontally. Does anybody ever do rotated bounding boxes?
Yeah, so there's this ridiculously strong tradition in axis-aligned bounding boxes, and that's not how the real world is at all. They're just so easy to work with. Yes, people do it sometime. I was literally Googling this today because it matters in my work. there's this issue, or there's this GitHub issue in this one repo where they've clearly spent months and months and months trying to implement this. Because basically, like, every single component that touches bounding boxes needs to be rewritten in a more complex way so that it handles this, like, boxes with rotation, essentially. So yes, it does happen, but it's brutal. I don't recommend it. And so, so we consider these thousands and thousands of anchor boxes just peppered over the image. I have this kind of visualization I put here, which doesn't do it justice. But if we did do it justice, it would just be full of pixels. It would just be black with bounding boxes. And for every single one of these, we ask, like, what is the probability that there's an object of interest in this box? And if you had to adjust this box so it was in the right place, how would you adjust it? You'd move it up and down and scale it width and height, basically. And from that, we get a whole bunch of boxes that we can cull down to the boxes that we're interested in. So we probably throw in a threshold and say, I don't want to see anything that's less than 50% chance of having an object. Or I think more commonly, give me the 1,000 best bounding boxes. And we end up with this kind of set of proposals. That's the term you would use here. We set a proposal. And so maybe we have a box here on the basketball that's like 85% chance of being of objectee. There's a 90% chance there's an object here, maybe 70 down here. We then take these boxes and cut out the piece of image that represents them, and we pass them to another sub-neural network that refines the boxes. So it takes this initial work and it says, okay, if I were going to make this box better based on the detail right here, what would I do? And so we can adjust these boxes so they snap to the objects better. That's the idea. We're not done yet. We're now going to take these refined boxes, which I guess I screwed up that box a little bit. We cut the contents out. We resize it so it's this kind of standard size, and that does mean warping the image, which, like, it's counterintuitive that you do this, but if you do this all the time, even during training, then your network learns to handle that. And for all these standard sizes, we do two things. First, we come up with a classification. So maybe this top object is like 80% cat, 20% flying squirrel. And then we look up the cat masker for segmentation, and we get a model to assign a class. So another sub-model, there are so many in here, to assign a pixel class to each pixel as to whether or not it's cat. We do the same thing for basketball, maybe, and then maybe we have this pylon at the bottom. It's been misclassified. Fine, our model's not perfect. It looks kind of pylonish. The cat is making him look like a pylon. He's so good at basketball. And then finally, we have to map all of this data back onto the original image. So there's a bunch of math to be done there to put the masks in place. A little more real-world example. This comes from the Matterport mask RCNN repo. It's kind of a big deal. 16,000 GitHub stars. That's a lot. This is actually from the README, so it was easy to find. So these are a bunch of these kind of like proposals that were good. So these are like the good proposals. This is what the proposals look like once you refine them into being like actual bounding boxes. And then these are the like masks that you might create after cutting a little square out and resizing it. You can see the aspect ratio gets thrown off a little bit here because people aren't square, but the model's expecting square inputs. And then we kind of map that back onto the data. You get something like this. You can see there, like, confidence is written on there as well. So that's what. Oh, Matt, I saw you.
Yeah, can we go back to the cat slide?
Yeah, well, there were a few cats.
And not just because I want to look at the cat. So in the top middle box, you say the first one does a classifier that says, is this little box a cat or not? We determine it's a cat. You said it passes it off to another submodel. Is there a different submodel per class?
Yeah.
Like, there's a cat-specific submodel,
yeah,
and then there's a basketball-specific submodel. Oh, wow.
That's not always done. Like, I've seen stuff where it's just like a single model that's just kind of saliency or find the object in here, but I'm pretty sure they have a different one for every class. Now, in training, it's kind of, you just look up the one you want. Sorry, in inference, you just look up the one you want. In training, it's a little more complicated. Everything in here is more complicated with training. But you could imagine naively and wrongly, but that's fine, doing the forward inference procedure and then computing a loss and backpropping it. It's different from that, but not so different, I guess.
Yeah, I feel you need a lot of data, even per class. Like, the risk of overfitting to a underrepresented class here is really big because you're defining a model for each one, right?
Yeah, I agree somewhat, although I'll say in my experience, bounding box data and segmentation data piles up faster, hand wavy, than classification data. Because like if I give you an image and I say this image level, the label is dog, like there's a lot of features in that image that you can kind of overfit to for dog. But when you're finding boxes or finding pixels, in a way, like every single box is a data point or every single pixel is a data point. So it's actually quite much richer. Um, so uh, like if you told me you wanted to do classification with 1,000 images, I would worry. But if you wanted to do segmentation with 1,000 images, I'm like less worried.
Would you be less worried if like the typical like dogs can take many different colors, right? And so maybe like it won't overfit to like that specific, or maybe it would overfit to like that specific color of dog. So you need a lot more dogs to represent kind of like all the different types of dogs there could be. Whereas some other objects are kind of a simpler, like a basketball is always orange, so it'll be, you don't need much data to do that. To do that.
Yeah, I think there must be some like broad observation here about like the broader the distribution, then maybe the more data you need to cover it. And if it's a broad distribution and you don't have much data, then your data points are more likely to be kind of isolated and easy to overfit to. Hadn't thought about that before, but you make a good point. Right, and so this is further evidence that okay, this stuff is complicated and hard. So detection is the standard PyTorch library for doing this kind of thing. This is a config file for BaskRCNN with a ResNet 50 backbone and a feature pyramid network from. This is basically the standard BaskRCNN from that repo, and this is the model. Like these numbers as a group define the model. And like, wow, there's a lot of stuff here. So there's this like backbone, that's the underlying convolutional neural network. There's this feature pyramid network that just makes the features better. There's this region proposal network. That's the thing that creates the thousands and thousands of anchor boxes and then like adjust them and gives them scores. This up here is the bounding box. This cuts the pieces out of the image and resizes them for later. This is the thing that like fixes up bounding boxes to make them even better. This is the thing that pulls the pieces out for masks, and then this is the thing that finally predicts masks. Lots of pieces, and it's not over. There's another slide. So this is not for the model, but this is for training. So all of this is parameterizes the training process, and there's all kinds of hyperparameters in here that I don't recommend tuning. I think a lot of them don't matter a lot. It just matters that the algorithm kind of exists. And like again, these are big slow models, so you're never going to be able to try a bunch of different things. Yeah, there's an indication. Right. So here's the leaderboard, final leaderboard for the competition. I think one thing I wanted to highlight here is the scores. Oh, go ahead.
Yeah, can you go back to that previous slide?
Yeah.
So when you say you can never try out a bunch of things, so what do? You just choose parameters that seem to make sense because you have previous experience? I can't hear you.
Alexei, we've lost your audio.
I'm back. Yeah,
you are back.
Okay. So somebody else with a lot of resources and time, like did some of this for us. Like they're authors of the paper and people who work at Google and things like that. And so these numbers are kind of they're the default here in this config, and they're probably the numbers that were used for the best results in that paper. That's a great place to start from. And yeah, like I think if you spent time to study like each of these components and like what it is that they do and how that works, you would be able to form some intuition as to if my problem is different, then maybe I should pick a different number. It's very hard though. These things are very like abstract, and so we usually settle on an empirical method where we just try things and then pick the one that has the best score. That's how a lot of machine learning is done. But like that's very hard to do in this case because of the number of possibilities and the cost of trying one.
Thanks.
So these parameters are for a model. Would this be like for the cat model, and then you might conceivably have a different set for the dog model or the basketball model or whatever?
No, this is like the entire mask RCNN network. Like if I roll up one, like the 81 here is 300 for open images, right? And that 81, and it's like in more than one place, which is nice. Don't repeat yourself.
Right.
Right. So on the leaderboard here, I was going to highlight that the scores are around 0.5. So this is a hard problem. Those are lower than scores that people score on other problems. Reasonably tight. This top row, the first place, these are academic researchers. Second place is more like Kaggle Grandmaster. I like the fact that they reversed positions. So the public test set, I guess Noise was first, but when they finally used the private one that nobody got to overfit to, he fell down to second. So that's unusual and pretty big deal. Here's again not my slide. So this is from the conference. 193 teams, but actually only 45 of them made any kind of results that you would count as like a decent attempt. People used a kind of external data sets like you might expect. They used deep learning frameworks that you would expect. Highlight detection was used a lot. And people used, they say, like they make a list of basically every model architecture you could possibly conceive. So sure, fine, people use them all. Some observations they made. Some people made big ensembles. That's how people try to win competitions. People did a lot of different things to handle class imbalance. I think they pointed out they found that teams were generally conscious of this compute time. So, so for example, if you're trying to figure out what method is best for dealing with class imbalance, like don't use a big, heavy model on all of the data to try different methods for class imbalance. Try something small and fast. You're not going to get the best results with it, but that's not the point. The point is to find out what's the best method for class imbalance. And those two ideas are probably not coupled. Like if you change the model, you probably don't need to change your class imbalance method. And I can't justify that. All I can say is my gut tells me that's the case, and other people with guts agree with me. So it must be true. But they observed that. And then again, they mentioned like you see a lot of MO detection. I'm not familiar with TensorPack. I'm a PyTorch guy. I presume it's TensorFlow. If anybody wants to chime in, go ahead.
I don't know about TensorPack. I was curious about the ensembles. So how would you ensemble data like this? Is it like a majority vote for each pixel or something?
Yeah, you at the end of the day, you have a bunch of you have confidences for the entire mask, but it's also like a sigmoid at the end of your segmentation network. So for every pixel, you have like a float value. So you could make them hard and do pixel voting. You could average them. We might get to it. Second place had a very interesting ensembling method that I don't totally get, but there's a really complicated diagram. So first place solution are these guys with fruit. Well, actually, there's potatoes. So they're kind of fun. I'm pointing at them right now. My wife just earlier pointed out to me this is like Fruit Ninja, if anyone's played that game. It's a great game. So there are three of them, and they are from the Multimedia Laboratory from the Chinese University of Hong Kong and the Multimedia Laboratory of the Hong Kong University. I'm just going to show my ignorance. I'm just assuming that this is correct, and those are two different universities. But and then somebody from SenseTime. I will point out that at least one of those MMs is the MM from MM detection. So there's a tight connection there. They have slides which I have the link for. Unfortunately, they had a presentation. They gave it with some slides at the conference. They didn't provide a write-up, and the slides don't present themselves. They did use that pixel-wise voting though, so you were onto something there, Bruce. And yeah, they did something with instance detection and saliency segmentation. I think maybe they had only one segmenter and not one for every class based on this, but I'm just guessing. I assume that they're writing up their results as we speak because they won, so they must be good results. It's got to be publishable. I was just going to point out too, yeah, detection, 8.7 thousand stars on GitHub. That's pretty good. Interestingly, not as much as that Matterport that nobody used, but maybe it's like a reference implementation. Then we have second place, so friendly face from the Kaggle world, Kaggle Grandmaster. He's like an ODS guy, I guess. Noise, I assume is how I would read that. So he used this thing called hybrid task cascade mask RCNN. And he had some slides we might look at later. He also used detection, so that's another good sign that you might want to consider it. All right, so what did he do? So this is going to be like pretty high level. I mean, I have to admit, I'm only understanding it at a high level, and there's like all of these things just have zillions of details under the hood. But so here we're going to build this up. And by the way, like this is broadly how I recommend learning about this stuff. So like if you want to understand hybrid task cascade mask RCNN, you should probably learn cascade mask RCNN. You should probably learn mask RCNN. You should probably learn faster RCNN. You should probably learn fast RCNN. You should probably learn RCNN. It's all stacked all the way back. It's really amazing how like perfectly stacked it is also. And so it's a long series of papers. I have a link at the end, the Stanford CS 231 or whatever lecture notes. I actually do a really good job of building that up. And then you can also read the papers in sequence. So here in this diagram, they're building this concept up as well. And so on the left, we have this like basic faster RCNN architecture. This is for bounding boxes, not for masks, but actually mask RCNN is built straight on top of this. They're tightly related, hence the sort of layer-wise learning of all these things. We take an image, it goes into the network. We have something that computes this C0, which is our like objectiness score. What do we think the chances that there's something of interest in here? And then these B0s, which are our proposals. Those are the like slightly better than anchor boxes. We then extract data from the image. That's this pooling layer. So we cut pieces of it out. And then we have this second like module that classifies them and then refines the bounding boxes. This is the basic faster RCNN. If we wanted, we could do something iterative, where it looks like before. By the way, they've omitted C0 and H0 from the diagram, but they're still there conceptually. They were just saving themselves space. So we could take those proposals, we could cut them out, we could refine them, but we then have boxes we could refine again if we wanted to. So we could actually take these boxes, put them back in, refine them again, put them back in, refine them again. Do this iteratively, using the same network every time. That's why it's labeled H1. So this is something you could conceptually do. C, integral loss, don't understand, don't want to talk about it. But jumping to D, cascade RCNN, it looks like the iterative, except the difference is it's a different network each time. So we're going to take the first refinements and refine them again, but we're going to do it with a model that's specialized for refining things that come out of the first one. And then we're going to refine them again. So this would be a cascade. And so if you do this, you might get better results. I guess they probably did. So it's an interesting idea. Ives.
Yeah, that last one, the last one, and also the iterative. Like I don't know, like I do have the feeling that this looks quite a bit like a multi-resolution analysis in wavelets, like this stacking. What I wouldn't expect is just like always the input image going. So I don't know whether that sounds like it makes sense, or so I'm actually curious to hear about this hierarchical version, because starting to get the feeling that it's going to look quite a bit like a structure of a wavelet filter bank.
Well, let's see. So here's another diagram. Unfortunately, the visual language has changed. Looking at you, data visualization. Sorry, on my screen, you're right there. But so this is hard to get, but I mean, they're from two different papers, and there's no standard. Sorry, I shouldn't be pointing. I should be using the Fruit Ninja slicer. So up in the top left here, this is Cascade Mask RCNN. So we've switched from bounding boxes to mask world, which is a little confusing, but it's still basically the same stuff. So this is what it would look like. This is essentially the same diagram as, so this last one here, it's the same, that just the boxes have changed names and colors. And so there's different ways you could do this if you wanted to. So here in this interleaved execution, we could take the proposals, we could cut them out, we could refine the boxes. But why would we use the old crappy boxes to compute the first mask when we could use them. We use the improved boxes to compute this mask. And so just by shifting the arrows around, which is just about passing different data to different functions, we should be able to compute masks that were based on like better boxes. So there's just one improvement you could consider. You could also consider, I guess, residual connections, essentially, where instead of computing a new mask each time, we compute a change on top of the old mask. And so now these models are not just each single one of them trying to come up with a mask all on its own. They get to be a bit specialized for filling in the mistakes of previous models in the masks. And then finally, there's this. And this is the conceptual diagram, and I'm not going to be able to go much further than that. This semantic feature map should be what's going into the region proposal network, but for some reason it's on a different path here. So maybe it has its own convolutions or something. But what matters is that we actually are able to line up features in the mask space. I'm sorry, Yves. I don't know this one. I also don't know about wavelets.
Yeah, it actually sort of looks like when you added that when they added that RasNet like update on the mask over there. So like when you mix both that up and down with that residue on top, it kind of looks like a wavelet. I have to put some thought into it.
Me too.
It's tricky to understand this diagram.
And so that was the method. I just wanted to highlight this. I mean, this was like a very researchy competition. Like not many participants, lots of academics. So there's a lot of really interesting and good solutions. Like the leaderboard wasn't a blowout, but I'm sorry, I'm not talking about them because we have like limited time. I was going to come back and click this, which you guys probably can't see, or can you? You see the PDF? All right, good.
Yep.
I was sharing Chrome or something. This is Noise's slides, which present themselves kind of interestingly. There's some accessible content in here. One, he talks about data filtering. So this is a couple of examples that might be a problem in the data set. We have labels for mouth and labels for person, but by no means are all the people or all of the mouths labeled. And so this could be a problem. You might want to filter these out. He says he kind of had this little algorithm he wrote where basically he's making sure that like we only really want to keep images that have a lot of things labeled in them because they're probably not missing things. Basically, these are probably better images, but we don't want to end up losing our rare classes. Class spelled with a K tells you something about his other tongue, presumably. But like this is a way of pruning down the data set. And you know, basically what is a rare class? Like maybe there's different ways of defining that. In this way, he actually filters away a bunch of training data, which makes us sad, but at least the stuff that's left over is better. He also observed that there was a very large validation set, and we didn't need to have all of that, so he chucks a bunch of that into train. It's a good Kaggle move right there. Don't be an academic and just accept the benchmark rules. Train on all the data you can get your hands on. Two concepts here that I didn't look up in detail, but anyone who wanted to learn more could look at. So something called class-aware sampling. He has a reference. IOU balance sampling. He has a reference. So fine. He used albumentations, which is, by the way, great. I use albumentations. It's a great library for data augmentation, and Kagglers love it. It's from Kaggle for Kaggle, by Kaggle. Kaggle people make that. He used detection. He used hybrid task cascade. He had an ensemble with crazy backgrounds. Backgrounds doesn't really matter. What I thought I would highlight, like I'm just running through his slides, but I thought was interesting. So he actually took a model that was pre-trained on Cocoa, but hacked it up. Because Cocoa's on like 81 classes, but there's like, we need more classes, so what are we going to do about this? So he did a bunch of stuff of reshaping the weights to have like this badly pre-trained model rather than starting from scratch. Without going through the details of his training procedure, I think the interesting fact here is that he had one. Like people who teach ML like to talk about freezing parts of neural networks and training other parts. In my experience, that's basically never a good idea. Like I've never seen a complex freeze, unfreeze, gradual, whatever strategy come up with better results. And this one's quite complex. Like this visualization on the right tells you everything you need to know. But like there's this and then that and this and then that. But I mean, it worked, obviously. Also, you've got some resources. There you go, V132 gigabytes. It's a big graphics card. And then finally, if we did want to dwell on something, he did something complicated for ensembling. If you tried to make sense of this diagram, you might eventually get there. At a high level, what he's clearly done is he's ensembled stage-wise through the inference procedure. So rather than take every model and just run them through their conclusion, and then taking their final predictions and merging them, you could actually at various stages through the inference, take the proposals. Maybe you ensemble those in some way. Take the refined bounding boxes and then ensemble those in some way. And finally, so at each time you're using like the best possible bounding box to make the best possible mask, rather than maybe mediocre bounding boxes for mediocre masks. So it's an interesting idea. He doesn't report like, how what the what a baseline comparison is. So we don't know what a basic pixel voting ensemble would have scored with his models, but we know that he did this for his winning solution. But I'm not prepared to talk that in detail, and we're also running late on time. So this essentially concludes my presentation. On my last slide, I have, for anyone who wants to start to try to access this stuff, if you're brand new to computer vision and convolutional neural networks, you've probably got some things to learn from other places first. But if you do know those things and you want to get into object detection, like this is the hierarchy that I would send you to. I don't think you need to study RCNN and those other things that you could jump in at fast RCNN and these papers in this order. Wow, that's a lot of citations, people. 8, 16, 5, archive links. And then finally, I do feel like this set of lecture notes in particular does a good job of building it up. It builds it up even from like a more basic level. So like partly kind of historically, how did people solve this stuff before deep learning? But also kind of like about like naively, Like so for example, if I understood training dog classifiers and I wanted to find a dog in an image, what I might do is cut that image up into chunks and try to classify every single chunk of that image. And the chunks that got a high dog score are probably dog chunks, and the chunks that didn't are probably not. And that would be like a first step towards finding dogs and labeling pixels as dogs. And they do a good job of that in those lecture notes to help you kind of, in your own mind, build up the complexity of a solution. So anyway, yeah, like I said, that's the conclusion of my presentation. We took questions as we go, but we should take questions at the end. And also like discussion, right? Because I'm definitely not a renowned expert on this stuff. So
I'll start off with questions. So near the beginning, you said if you had your own hardware at home, maybe like a $2,000 computer, you could dabble in something like this. Can you maybe talk about like what is needed to actually solve a problem like this and actually be competitive?
Good question. Like competitive, I think with probably more like $5,000. I'm thinking you probably want two like modern, like kind of 2080 GPUs into a machine. It needs to be able to process a whole lot of images to feed that training process. So that would be like where I would ballpark it. People can feel free to disagree with me. Like the people, I think, correct me if I'm wrong, the evil people at SenseTime probably have like 4 or 8 GPUs in these ridiculous machines that they use to run their experiments. So I think that's what really serious business, and I don't know. You have a DGX at work. How much did that cost?
Yeah, I have a $100,000 machine at work that's still inoperational or not operational.
Shut up! Shush! The stock is low enough.
Yeah, they'll just sell it.
And so there's an indication.
So I have a question. You may not want to answer this, but if you can tell us something, I'd be interested. So I think you indicated somewhere along the way that this type of algorithm is relevant to what you're doing at your job. Can you tell us a little bit more about what robots that your company is involved in and why this might be relevant?
Yeah, sure. So we're working on robotics for automation with a focus on automobile manufacturing. And as you might know, there are a lot of robots in that space already, kind of famously. But there's still like lots of jobs that people are doing, and like really awful jobs. They're like picking up objects in a slightly chaotic environment and then placing them so that the machine can do the next task. And if you're going to stand there and do that all day every day, yeah, it sucks. And so like I'm very interested in using vision to find like objects in a somewhat unstructured scene and separate the instances from each other so we can go pick them up, basically. And I'm not just interested in classification or even detection, but I would like a really precise pixel mask of like a bounding box isn't good enough because my robot needs to be able to reach in and pick it up. So we need to be very accurate. For some types of picking up and from some types of parts, I think you need to be very, very accurate. Otherwise, you miss or you fumble it.
So you would care a lot about orientation, for example.
Yeah, absolutely. Right. So like a pixel mask, like it's not a pose, right? So it doesn't have orientation, but it sort of does. Like if I have a long piece, like a long object, and I have a pixel mask, like I have a pretty good idea of its orientation. Whereas, yeah, like a bounding box is nothing. And in fact, if you have a long sorry, my work is slipping through. If you have a long object and it's at this angle, the bounding box is basically a big square around it. You got really, really poor information about where it is if you do it at that level. And so that's why instant segmentation is important. Other questions or items for discussion? I think the visual relationship thing is probably really interesting. Like I think if someone were looking for something to present 2 weeks from now, especially given that everybody here has been introduced to the open images dataset, I think that's potentially an interesting competition.
Is that sort of like what Karpathy did for his thesis work, where he has an image and he analyzes the scene and writes a narrative about the scene based on, I think, partially on the relationships of things in there?
Oh, is that his stuff? Yeah. Like image
Fei-Fei Li does a lot of that, and that was his work. Yeah.
I don't know.
I'm sorry, I have a question. Was there anything about the performance of these models, or it was just about the precision and those metrics that you talked about?
You mean like in terms of speed, basically?
Yeah, like performance-wise, did they compare any of the models there? And I guess in your line of work, you'll need a real-time performance. And here, those models are probably way too far from real time.
Yeah, no, you're absolutely right. So like there was no requirement for speed and no measurement of it in the competition. And yeah, these can be pretty big and pretty heavy. I mean, certainly like all of these model architectures scale in the sense that with the same basic idea, you can have a bigger one or a smaller one. And so they naturally, in an environment where speed doesn't matter, they all picked bigger ones. But smaller ones can run fast. Actually, there was an efficient det, by the way. So everyone's heard of efficient net. Well, not so. There's an efficient det that Google made. I think they just open sourced the code, but the paper's older. Yves is nodding vigorously, so maybe he knows more about this than I do.
No, I just know they released it like this week, I think.
Yeah, and it's probably a bounding box model, but extending these things to masks, you could just figure out how they extended mask RCNN and then just apply that to that. The warning, by the way, while we're on this topic, is that like the details, the devil's in the details when it comes to speed, and like if you just take something that somebody said was fast in their environment and try to use it in your environment, it's not necessarily going to be fast. And like a great example of that is the efficient nets. Ross isn't here, but Ross has done a lot of testing on those things, and it's amazing just how basic desktop GPU architecture and like the tech stack of CUDA and cuDNN and stuff like really likes ResNets, even though they have maybe more flops and more parameters than the efficient nets. They might still be faster sometimes. Eves is nodding; he might have more to add.
Yeah, efficient net. I believe it was optimized for TPU architecture.
Yeah, so I'm probably not about to pull efficient det off the shelf and find it works wondrously for my robots.
My guess is it was also optimized for TPUs probably. But so one thing that I do wonder is like for just vanilla bounding box prediction, like object detection. To what extent it actually makes sense to use these much larger, much fancier methods. Like we, in my team, we just use YOLO and SSD in production, and does a pretty bang up job. I really don't see us ever moving into something like this big because we already have like some issues regarding TPS just for like models like SSD and YOLO.
Yeah, I mean, I'll echo that. Like in my last role, we had an object detection like microservice component in our application, and we used an SSD, which is like single shot detector. Never mind what it is, but it's smaller and faster and simpler than these models. And even then, also like I think resorted to a ResNet 18 backbone to get it as fast as we wanted. So we were already even making, and we were not in a super constrained environment either. We weren't like running on a phone or something. We were running on Amazon servers. But even then, like so like I agree. Maybe for a lot of practical applications, these are overkill. Unless you're in an offline asynchronous situation where precision really matters. I don't know, like processing
but even
satellite
in that case, you
images.
still have to pay for the inference, right?
Yeah.
You still have to pay for the inference. Like in my team, we do just run stuff. Up until recently, we were just using C5 instances on AWS, and recently, we doing some benchmarking, but might be moving into G4, I think, G4 instances, because like cost benefit. At the end of the day, like you still have to pay for the thing.
Yeah, and you brought up something that I'll point out there. Like, so if you have like a classification neural network, I think those tend to run decently fast on the CPU at inference time. But in my experience, these models run really slow on the CPU. I think
the GPU.
They run slow on the CPU.
Yeah.
I think like there's a lot of high resolution images in the network still. The feature pyramids are huge, so you really need the parallel processing.
Yeah, I think like in any case, whatever is your actual end application, assuming that you're going to be paying for it, you really should just run benchmarks. Because I remember before the G4s, we had like G3s and the P instances, and we run benchmarks that in the end of the day, like the best cost benefit for us was just using C5s, C5 instead of C4 because of MKL, the Intel optimized library. But when G4 came out, the cost benefit like severely moved to G4. So I'm pretty sure we're moving into G4 very soon.
And so it's kind of like the training configuration in that.
Oh no!
I know. Sorry, but like the one that I presented earlier, in that like it's pretty hard to guess ahead what's going to be best, and so what you do is you try them and then you figure it out.
Yeah, we just train on P3s.
Yeah. And then there's other factors when you're in production as well, like in AWS, depending on your situation, you might have a dedicated instances or spot instances. So spot are there's a marketplace for them. If you work at Amazon, then you probably get a better price than the Spot instances. Or maybe you price them internally at Spot. That would be rational.
That doesn't happen, believe me. It's just Amazon is just a big customer, the biggest customer of AWS.
I noticed Dan put on his video. Is that because he's going to ask a question? No, I can read lip read. So we hit 8 o'clock, so we're late for our reservation at Rogue. I don't know. Are we gonna do the speed dating thing, Bruce?
Well, let's do one thing first. Bruce,
Grab a beer
for you to unmute everybody, or can I get everybody to unmute themselves for a couple seconds?
I know what you're gonna do there.
Can we give Alexia a round of applause for today?
Thank you.